Now that we can do reactions with benzene, we want to look at different strategies for making monosubstituted aromatic compounds as well as polysubstituted aromatic compounds. So we can start with benzene, add bromines and chlorines using bromine and chloride with the corresponding aluminum compounds. You could also use iron in place of there. We can add nitro groups, which can then get reduced to form aniline. We have sulfonate group that we can add using fuming H2SO4. We can add alkyl groups, which can then get oxidized to carboxylic acids, or you can brominate it using excess NBS, which turns this into an electron withdrawing group here. And we can also add acyl groups, which can then get reduced to the alkyl group. If you have to worry about a rearrangement, we can add that acyl group and then reduce it. We can change the directing effects based on the group. If you have a nitro group, that's a meta-director because it's electron withdrawing. If you reduce it using zinc, we now have aniline, which is an ortho-para-director. The same thing with the alkyl group that you're adding using a Friedel-Crafts reaction. This is an ortho-para-director. If we oxidize it to carboxylic acid, that makes it a meta-director. Adding an acyl group is a meta-director. Reducing that to the alkyl group is an ortho-para-director. And you can also do the same thing. We have this ortho-para-director. We add excess NBS, which will do the benzylic bromination, and that is now a meta-director. Nitration usually can cause amine oxidation, which leads to extra products that you don't want. So you don't want to do a nitration of an amine. Friedel-Crafts reactions are too slow to be practical when you have a deactivating group on the ring. If you have any electron withdrawing groups on the ring, we're going to see no reaction here. And likewise, if you have a strong deactivator, this electron withdrawing nitro group, this is also no reaction. Friedel-Crafts also do not work with strong electron donating groups. So things like an OH or NH2. Design a synthesis for this molecule below, starting from benzene. So observations that you can make is that we have 2 carboxylic acids. They are ortho to each other. If you had one acyl group, that would be a meta-director, or this carboxylic acid is a meta-director. So we probably had an ortho-para-director on there before we added the second group. And we need to form carbon-carbon bonds. Okay, so if we're starting from benzene, and I'm just going to work backwards here. I could have made this from something like this and then oxidized it, which could have come from there. And that goes back to benzene. So I start with benzene. I'm going to do a Friedel-Crafts reaction first. So I need to just add CH3Cl. And really you could have added extra carbons here, because if we do the last oxidation step, that will cleave everything off except for the benzylic carbon. So once I do this reaction, I get my methyl group. And this is an ortho-para-director, which means I could get both products, but I really want to ensure that I have only the ortho. So I'm going to put a blocking group on there. And then I'll do my next Friedel-Crafts. And now that we've blocked the para, it will go to the ortho position. Now I'm going, this was still here as well. And then I can add dilute H2SO4. In order to remove that group, and then KMNO4. And that's how we can do that synthesis. So when you're designing a synthesis for a polysubstituted aromatic compound, again, you want to do a retrosynthesis, which can be helpful. And look at the relationship between groups to each other. If we look at the relationship between these groups here, these are meta to each other, and both of these are electron withdrawing. And this bromo is ortho directing, and this nitro group is ortho to the bromo. So I think I want to put the bromine on here first, because then we have a bromine with a para group here and an ortho group there. So if we're looking at the retro here, I can put the nitro group on last, and I want to do my bromine first. So if we start with benzene, this will add my Br. So the bromine is an ortho-para director. I'm going to add this other group here next. And when you're looking at what to add, just take whatever's on the other side, the carbonyl plus everything else, and add a chlorine. And I'm going to add this para. And right now I have this activator and this electron withdrawing group, which is a meta director. In this case, if you have two things directing, the halogen always loses. So the acyl group will direct. In this case, it will be directing meta to the acyl group. And we get our product. If we had put the nitro group on before the acyl group, the Friedel-Crafts acylation would not work. And then if you had put the acyl group on, that would have been a meta director, and you wouldn't be able to get the bromine ortho to anything. So these are things that you want to think about when you're doing synthesis of aromatic rings. In the next section, we're going to look at nucleophilic aromatic substitution, in which the benzene ring is going to get attacked. So aromatic rings generally tend to be electron rich, which allows them to attack electrophiles, which is what we've been doing most of this chapter. In order to facilitate an attack by a nucleophile on the benzene ring, the ring has to be very electron poor. It has to have a good leaving group, and the leaving group must be ortho or para to the electron withdrawing group. In this situation, we have a leaving group, and we have an electron withdrawing group that is para to the leaving group. When we do this reaction with sodium hydroxide and heat followed by acid, we get an OH. So this is doing a nucleophilic attack. So if we look at the mechanism of why this happens, we have an OH minus that's going to attack where the leaving group is. These electrons will go on to here. If we have the negative charge on the carbon, which through resonance can add that negative charge to this here. If we have this electron withdrawing group in this Mesenheimer complex, that can pull electron density out to stabilize that anion. And you can see the further stabilization through resonance, and because the oxygen on the nitro group can pick up some of that electron density, and then you can draw these electrons back in where the oxygen pulls electrons in to kick off that leaving group. So in this reaction, if you tried to do it with chlorobenzene and sodium hydroxide, this is no reaction because there is no electron withdrawing group. If you want to do this reaction without the electron withdrawing group, we have sodium hydroxide with extreme heat. So this is 350 degrees, and that will get you your phenol. Or you can use it with an extremely strong nucleophile. So this sodium amide will get you NH2. The way that this reaction works is we have this chlorine is labeled to show how this mechanism works. The sodium amide, or the NH2 minus, is going to pick up a proton, leave the electrons here, which can go in to form a triple bond and kick off the Cl. So this is a benzyne that is created. Once we have the benzyne, the NH2 minus from the sodium amide can attack the benzyne at this position So these electrons will come onto here. We get a minus charge. There's ammonia floating around. We get a proton transfer. So this is the product you see here with the NH2 on the labeled carbon. And this is an equal opportunity alkyne. So this NH2 can actually also attack on this side. And we can get a proton transfer here. So these are the two products that you would see in this reaction. So here are a couple of practice problems. Reacting benzene with tert butyl chloride will give us the tert butyl benzene. This is the Friedel-Crafts alkylation. If we have a nitric acid to here, we're going to get a nitration. This is an electron donating group. So this is an ortho-para director. So we're going to get ortho plus para. And if we have the carbonyl coming off of the ring, this is a meta director because it's now electron withdrawing. The next slide here, we're going to add reagents to get the synthesis to work. In step A here, we actually are going to need a couple of steps. We have a bromo that is meta to this alkyl group. Alkyl groups are ortho-para directors. This is an ortho-para. And this is also one that is a primary chain, so you'll probably have to use the acylation first. So I'm going to add the acyl group. I have 1, 2, 3 carbons. AlCl3. And then add the bromine to make sure it goes meta. And then I'll do the reduction. In B, I have the carboxylic acid, so I'm going to oxidize using KMnO4 plus water. In this step here to get C, I have HNO3 plus H2SO4. When you have bromine versus this one, we'll get an ortho addition or para, and I think space-wise we'll probably get the para product. Which also happens to be ortho to the bromine. The zinc HCl is going to reduce the nitro group to an amine. And that bromine is still there. To get to E, I see we're making an ether, so they're probably doing a nucleophilic addition here. So we can add NaOET with heat, and this should work because we have the electron withdrawing group ortho to the leaving group. Alright, so on this one we want to propose a synthesis for the following molecule. A carbon source can have no more than 6 carbons. Any other reactions can be used. So you can try and work on this for a little bit before you come back. The synthesis that I put together is a couple of steps and it requires 2 different parts. So if I just do a quick retrosynthesis here, I can think of 2 pieces here. I have benzaldehyde plus this Grignard. I'll start with benzaldehyde. I'll start with benzene and do a Friedel-Crafts alkylation. I'm then going to oxidize it. And then after I oxidize it, I'm going to go all the way to the alcohol, so excess lithium aluminum hydride, water, and then I'll oxidize it to the aldehyde using PCC. So that should give me the aldehyde. to make this part. I start with benzene. The bromine is para to the alkyl group, so I can do either of those in whichever order. So I'm just going to start with the bromine. And then I'm going to add the acyl part. And then reduce it. And then add the magnesium to make the Grignard. Then we combine these two together with water to give you the desired product.